So now another idea was to increase productivity. What if I brought a washer and a dryer? Now I have two devices. Okay, so the first load, I'm gonna wash for 30 minutes and dry for 15 minutes. So this is 30 minutes and this is 15. Now when this finishes, I need to wash and dry again. However, this will create a problem that the wash and dry are not aligned. So I need to increase this to become 30 minutes so that I can have a typical wash-dry cycle that are synchronized. So now this is the first load, so this is dry. So I increased the dry cycle from 15 to 30 minutes. I just leave it idle doing nothing. So now when I want to put the second load, when I'm drying, I notice that the washer is free, so I can put the second load here. So I reuse the washer and then the dryer. So now I have 30 minutes for washing and another 30 minutes for drying. So now it's taking me a total of 1 hour and 30 minutes. Well, wait, well, this is the same as before. Remember when we had a single washer dryer, we had 30 minutes and then 15, this is wash and dry, and then we had also wash and dry. So this is another 45 minutes plus 45 minutes. So it's taking the same time. What if I have a third load? So now I cannot wash here. I need to wash while I am drying. So I add another wash and another dry cycle. So now I have total for 3 loads to be 2 hours. In my case here, I need to add another 45 minutes. So this amounts for a total time for 3 loads to be equal 2 hours and 15 minutes. So you see now I'm gaining time, and each time I add in another load, the advantage becomes evident that having 2 devices and reusing the device, not doing anything, will increase productivity by decreasing the time needed to finish my task. So this is called pipelining. Pipelining is the act of dividing a task into small problems and somehow reusing the components that are not doing anything to increase productivity. So in my case here, I have an increase in productivity by decreasing the time needed to complete the task. So this is called pipelining, which is reusing idle components to increase productivity. So this is the washer dryer example. So how can I apply this in my processor? So we said previously that the processor has 5 stages. So if you remember in my previous lectures, when executing an instruction, we have 5 stages. IF, which is the instruction fetch, ID, instruction decode. I have execute, which is the execution of this instruction, memory operations, and we have, this is memory operations, and write back, which is writing back the result to the register file in case of an R format or probably a load. So if I look at this, so typically here I have 5 different stages. So going back to the washer dryer, when I'm doing decode, the fetch is idle. When I'm doing execute, the component doing instruction decode and instruction fetch are not doing anything. So how about dividing my clock cycles into 5 stages? So the idea here, divide my clock cycle that I use for the single cycle into 5 stages. So in this case, each cycle will perform one of the operations, whether IF or ID and so forth. So imagine I have a big table. So let's say I have a single cycle. So I'm going to call this 5-stage pipeline because I'm dividing the operation into 5 stages. Remember this word. So with a single cycle, each instruction, as we said before, takes 1 cycle. Let's say I was able to measure the time needed for each stage. So let's say this takes 100 nanoseconds, this takes another 100, this takes 200, and again 300 nanosecond here, and this is 100 nanoseconds. So typically the total time, I want to calculate the total, so the time it takes to execute a single instruction will be 200, 400, 500 and 800 nanoseconds. Okay, so one instruction takes 800 nanoseconds. Now let's say I have a 5-stage pipelining processor. So here now I need, let us do it like this. So now what I want to do is I want to select the time I need to execute my stages. Remember, in a 5-stage pipeline, I have 5 clock cycles to execute a single instruction. So 5 cycles executes 1 instruction. Okay, so as you know, I cannot use different sizes for each clock cycle. In the previous one, in the single cycle, I just had 1 cycle. However, in the 5-stage pipeline processor, I have 5 cycles. Each cycle should be equal in length. So I need to choose one of these numbers to represent my frequency. So in this case, I'm going to use the slowest part. I'm going to use this guy to be my frequency. Why? This is because with the 300 nanoseconds, I cannot use a smaller one, because if I use a smaller one, then I don't have enough time for the memory to perform its tasks. So in this case, what I need to do is that all of these instructions will be the same. So now I have This will be, let me write in a different color. So this will be 300 now, 300, 300. All of them are nanoseconds, of course. So now the total is 1,500 nanoseconds. So wait a minute, how come you said pipelining is much faster when I have for a single cycle an 800 nanosecond time for an instruction, while I have a pipelining instruction that takes 1,500 nanosecond? The answer comes in not just doing a single load. We need to see more instructions being executed to actually see the gain of pipelining. As we see in the washer dryer, until the third load we were able to see a small difference. So let me give you this exercise. So given the previous values, which are these values, okay? So calculate the time needed for executing 100 instructions on a single cycle processor versus a 5-stage pipeline processor. So in this case, I take a look and I see that I have 800 nanoseconds for a single cycle. So let's take the case of a single cycle first. So this means one instruction takes 800 nanoseconds, implies 100 instructions will take 100 times 800 nanoseconds, which will be 80,000 nanoseconds. Now, let's take the case of a 5-stage pipeline processor. So, as you see, our frequency is 300 nanoseconds, or sorry, the period. So the total is 1,500 nanoseconds. So the first time, the first instruction, as it executes, it will take 1,500 nanoseconds. So instruction number 1 will be 1,500 nanoseconds. But what happens when I'm actually doing IF? I'm going to put another instruction. So if I do a time scale, I have IF, ID, EX, memory, and write back. So now this is the first instruction. And it will take, so this is the clock. It should be all equal. So this takes 1,500 nanoseconds. But as we said, with pipelining, when we get the second instruction, so of course, while doing fetch, I cannot fetch again, otherwise I will have parallel processing. I only have a single fetching unit. So what I do is, I start fetching while I am decoding, and I will decode while I'm executing, and do the memory, do the execute while doing the memory, and then memory again, and write back. So if this take 1,500 nanoseconds, then this will take an additional 300 nanoseconds. So if I continue with my third instruction, this will take another 300 nanoseconds. So we can see a pattern here. So for executing 100 instructions, the first will take 1,500 nanoseconds plus 300 nanoseconds times 99. So this is times 1. So you see the total here is actually 100 cycles. So now if I want to calculate the value 99 times 300, this will be equal to 1500 plus 29,700, and the total will be 31,200 nanoseconds. So you see we have a major advantage here, 31,000 nanoseconds or 31.2 milliseconds, and here we have 80 milliseconds. Okay, so this is equal to 80 milliseconds, and this is equal to 31.2 milliseconds. So we see here that pipelining has a major advantage for actually raising the speeds of raising the speed between having a single cycle which takes 80 milliseconds for a 100 instructions, and here it takes 31.2 milliseconds. In theory, a 5-stage pipeline should have a 5-fold increase when it comes to performance. That means it should be 5 times faster. However, since here we didn't use a uniform distribution for, or we didn't use uniform values for all of the stages, this is why we see this discrepancy. And if you want to see the speed up, the speed up attained here, we can say this is 80 milliseconds over 31.2 milliseconds, and here we can get the ratio of, that we calculated, 2.56 times faster. Okay, so this is the major advantage of having pipelining. It is reusing, if you go back, it is reusing components that are sitting idle so that we can increase productivity. Of course, this comes at the cost of added hardware. Okay, so we need to pay a price for this speed, which is in the form of added hardware and complications. And also this is true only for ideal cases. So what do we mean only ideal cases? So ideally, the speed up can be as large as 5 times for a 5-stage pipeline. However, this is not true, because sometimes we have dependencies. So with the washer dryer example, there's no two laws that depends on each other. So what we mean by here is that dependency drives performance lower than expected. Let's talk about what do we mean by dependency. Dependency, we mean by it is present values depend on past values. So if we have, let's say something like add $S0, $S1, $S2, and then let's say we're going to subtract and place in $S3, $S0, $S4. So if we look at here, what we're trying to do here is that we want, let's say this is 4 and this is 5, so the value here should be 9, and assume this is 6, and this was previously, let's say it was 7. Okay, so now it should be 9. So this, what we need here, we need the value to be equal to 3. So this is the correct operation of this. We add 4 and 5 in S1. So S1 is 4, S2 is 5, the value is 9. Previously 7 was inside S0. Now S0 is 9, the new value, and we subtract it from 6. So let's see how this works in a pipeline. So if we go ahead and set if id ex memory write back, and we place the second instruction. Remember, we cannot place if under if because if is already fetching this instruction, and this is time. So as I'm doing if of the second instruction, I'm doing id of the first instruction. So in this case, let's talk about each stage by itself. So this is instruction 1 and this is instruction 2. So with instruction 1, in if I fetch those values. In id I say, okay, s1 is equal 4, s2 is equal 5, and execute. I say the result equal 9. There's nothing to do here, but I'm gonna pass the 9. I'm saying the result is 9, and in the write back I'm gonna say s0 is equal to, it was 7, then it was replaced by 9. Now if I follow the same logic here by the second instruction, so the second instruction here, okay, so I fetch the result here, I need to fetch the values. So what happens is that I have s0, what was the previous value of s0? It will be written here. So it's still 7 when I'm doing decode, and s4 is equal to 6. Now the result will be equal to 1. The result stays here equal to 1, and then I have s0 is equal to 1, which is the wrong answer. So you see, when we have a dependency, then the pipelining fails to operate correctly. So this is called a data dependency, and this is called a read after write hazard, or RAW. So I'm reading here a read, and here we have a write. Okay, check this. This is the write, and this is the read. So this dependency actually is making things worse. So the simplest way they try to solve this is by actually stalling the processor. So what happens is that, okay, 1 will be if id ex memory write back. So as I fetch, I detect that I have a read after write hazard. So what I do is I need to stall, just inserting no operation. So I stall until id is directly under write back, and I'm going to explain why this works. So I fetch the first, I fetch the second instruction, stall id ex memory and write back. So here my delay was +2 cycles. Okay, so here my performance was decreased by just only 2 cycles from this. But remember, we have a very big margin of increase here for this 2 cycle to render pipelining useless. So actually those 2 cycles is just a small price we pay. This is why we say ideally, because we have usually we have many dependencies. So let's go ahead and check this again. So here we know that S0 will be equal to 9. So now in this case, remember, stall means no operation. I just insert no operations, and we're gonna talk about how we design this on hardware. So write back is in the write back stage of the first instruction, I have S0 equal 9, so in ID I'm gonna read S0 to be 9 and S4 to be 6. I'm gonna say the result is 3. Here I'm gonna continue with the result of 3, and here say S0 is equal 3. Okay, that's 3. So I haven't made a small mistake. This is S3, the value of this register. Okay, so here the delay was an additional 2 cycles. So it's very important when I have a dependency, a data dependency, is that the write back and ID to be aligned. So how did they do this? We remember in pipelining, so this is an important concept. So in pipelining, each component is used once in a cycle except the register file. So as we see here, each instruction, each cycle, this is the cycle, and so forth. So in each cycle we see that we're not doing 2 fetches at the same time. So this is the fetching unit, which is program memory. This is the register file, ALU, stall is not doing anything, and write back, and here I have the write back and ID. So they designed the register file in a way, okay, this is the register file, is that this is the cycle, and on the rising edge I will do write back, and on the falling edge I will do decode. So in this case, if I have here $S0 is equal 9, on the rising edge I will write, and on the falling edge I'm gonna say, okay, now I can read S0 to the correct value, which is 9. So this is the only component that can be used twice in a cycle, and it's utilizing the rising edge and the falling edge of the clock of this stage particular. This is why we are allowed to have a write back and an ID coinciding with each other and working perfectly. Otherwise we need to add 3 stalls, and this will add an additional cycle to our delay or our penalty for having a read after write hazard. So this is the data dependency. Of course we have many other dependencies. We have hazards, we have data, this is the data hazard, we have control hazards and memory hazards. However, we're gonna just focus now on data hazards. So now let's take a small example and work them out. So assume now I have the following program. So assume I have the below program. Okay, so I'm gonna say load T1 0.T0, then I'm gonna say add LW.T2 for T0. I have add T3 T1 T2, and I have SW T3 12 T0. Then I have load T4 8 T0. Then I'm gonna say I have add T5 T1 T4, and finally store T5 16 T0. So alright, I have this value, this program. So now I need to detect where do I have data dependency. So in the first one, I'm reading the value of $T0 and storing it in $T1. So now in the second instruction, I'm reading also from this value and placing in T2. So here I have no dependency between those two. Then I check here is that T1 has a dependency here and T2 has a dependency here, because here I have write T1 write on T2, and here I have read for T1 and T2. So here I have two dependencies. And then I check T3. Also, T3 is, there is a read after write dependency between T3 and this. Remember, SW reads the value and store it here. So this is a read and this is a write. T4, there is nothing in the destination about T4, so there is no dependency here. I have T1. Okay, so this T1. I noticed that this T1 also has a dependency, but does this dependency matter after so many instructions? We're gonna find out now. And now I have T5, which is another dependency. So if I look at this, I have a dependency T1, T2 on these two, T3 between add and the store W. Then I have T5 and another, and here I have a dependency. So if I want to place it with stalls, I'm going to do the following. So I'm going to just number them. So this is 1, 2, 3, 4, 5, 6, 7. Now, in order to know how many cycles I have, I will try and schedule this program in a 5-stage pipeline. So as we said, we start with the first instruction, 1, which is LW, and this will take, I will IF, ID, EX, memory, and write back. So we notice here that it's the first instruction. Of course, we don't have any stall since there is no dependency. We go ahead with the second instruction, and now we have, let's draw some lines. So with the second instruction, there is no dependency between T1 and T2, so we cannot start here. We start here next to ID, IF, ID, EX, memory, and write back. Now with the third instruction, we notice here there is a dependency between T2 and T1 and with the load. So the third instruction, I'm going to start it here. We have IF. We cannot do the IDEX directly. We need to add stalls. So this is stall 1, another stall. Notice here that in this, here we have T1 ready, and in this cycle we have T2 ready. So here we directly can say ID. So 1, 2, 3, 4, 5 cycles. So with the fifth cycle, ID will be perfectly fine since we have T1 and T2. T1 was ready in cycle 4 and T2 is ready in cycle 5, and we, as we said before, ID and write back can coincide. And then write back. Now the fourth instruction, which is going to be store, we notice there's also a dependency between 3 and 4. So we cannot start here, and stalls actually go down all the way, since in this instruction in this cycle we're not doing anything. So we're gonna start here. IF, of course we're gonna stall, another stall, and then ID, EX, memory, and write back. So now this is 6, 7, 8, 9, 10, 11. So this is the fourth one. Notice here we added those two stalls because we need T3 and ID coincides with write back, and we notice here that with store it needs T3. The fifth instruction does not have any dependency, so we're going to go ahead and start it, of course, here. IF, ID, EX, memory, and write back. So we are at cycle 12. We notice here there is no stalls because there is no dependency. Now we take a look at 6. With 6 we start directly under ID, and now we notice there is a dependency between 6 and 1. T1 here. However, T1 is ready at cycle 4 and I need it at cycle 10. So it's already updated its new value and I can perfectly use it. We notice here also that we have a dependency here. So this is also a read after write dependency because we're loading value in T4 and this requires a stall. So T4 here and there, so we need to have, this is 6. So this is, I cannot write ID directly, I need to have it a stall, ID, EX, memory, and write back. And now, so here we have also stalls, and the last one also we have stalls. So 7s, start here, IF, SD, ID, EX, memory, and write back. So 13, 14, 15, 16, 17, and 18. Okay, so to complete this program, I need 18 cycles. Typically, if I want to check the normal execution if there was no dependency, so in case of no dependency, so the first one will take 5 cycles, this will take 5, and then I will add a cycle for each one. 1, 2, 3, 4, 5, 6. So the total will be, this is 1, 2, 3, 4, 5, 6, 11 cycles. So as we said, we went from having 11 cycles to having 18 cycles by adding 1 stall, 2, 3, 4. So we added 4 times 2, which are 8 additional cycles. Okay, so okay, this is where I started from here. I should have started from, so this is 1, 2, 3, 4, 5, 6, 7, 9, 10, 12, 13, 14, 16, 17, 18, 19. So actually it's taken 19 cycles. So 19 cycles, because I need to start from here, I mistakenly started from here. So 19 cycles, and I could directly detect that I made a mistake because it is 11 cycles plus 8 stall cycles. So we notice that this is a big amount. So the question is, can I do anything about this? Now, the problem is, can I reduce the number of stall cycles? The answer is yes. I can use something called instruction reordering, something that is done by the compiler, okay, and it relies on moving instructions without changing program execution. Outcome. So this means I need to check which instructions are independent from other instructions. For example, I can switch T1 and T2 because they don't depend on each other, but this has no effect on instruction number 3 because both of them depend on this instruction. As W cannot move up because it depends on the value of T3. Now if I look at T4, now this instruction has nothing to do with any of the registers that is above it, so I can move it. So I have a stall here, so if I move this instruction and place it here, I can eliminate one of the stalls. And furthermore, since these two depend on each other, moving that instruction twice up will actually eliminate a stall between this instruction and this instruction. So let's see what I'm talking about. So first I'm gonna write the program. So this is the first instruction. As we said, the second instruction has nothing dependent, and moving it will actually will not do any good. 3, I will have the add instruction, or T2, and then if I look, I said I need to place this instruction, the fifth instruction, here. So under 5 I'm gonna put LW.T4. Well, I said I'm gonna place it here, so I'm gonna take this out and place 5 here, LW.T4 8.T0, then add 3 here, add T3.T1.T2, then I'm gonna continue with 4, which is SW.T3.0. 5 we already placed it. 6 I'm gonna add T5.T1 T4, and then 7 I'm gonna do something. So we notice here now that first of all the dependency between T1 and T2 is eliminated. T1 and T1 between 3 and 1 is eliminated. I still have a dependency between these two, but it will cost me just 1 stall if I place it on the not 2 stalls, because there is instruction between them. And then I will check if we have a dependency now between this and this. There's no dependency. Now here of course we have 2 stalls because between T3 and this one there is no more stalls between here, between this and this, and here we have 2 stalls. So we went from actually having 8 stalls to having just 5 stalls using instruction reordering. So we were successful in removing 3 stalls. So this is one major advantage that we can use to reduce the number of stall cycles. Of course, there are many techniques such as forwarding that we will use in order to reduce further the number of stall cycles, and this is what we will explain in the next lecture.